right, hey everyone, welcome back. So what we'll see today is additional elaborations on the EM, on the expectation maximization algorithm. And so what you see today is go over, quick recap of what we talked about EM on Monday, and then describe how you can monitor if EM is converging. On Monday, we talked about the mixture of Gaussians model and started deriving EM for that. I want to just take these two equations and map it back to specifically the E and the M steps that you saw for the mixture of Gaussians model to see exactly how these map to updating the weights WI and so on, how you actually derive the M step. And then most of what I want to spend today talking about is a model called the factor analysis model. And this is a model useful for data that can be very high dimensional even when you have very few training examples. So what I want to do is talk a bit about properties of Gaussian distributions and then describe the factor analysis model, some more about Gaussian distributions, and then we'll derive EM for the factor analysis model. And I want to talk about factor analysis for two reasons, because one is actually a useful algorithm in and of its own right, and second, the derivation for EM for factor analysis is actually one of the trickier ones, and there are key steps in how you actually derive the E and the M steps that I think you learn better or you master better by going through the factor analysis example. Okay, so just to recap, on Monday, we had talked about the EM algorithm, and we wound up figuring out this E step and this M step, right? And remember that if this is the log likelihood that you're trying to maximize, what the E step does is it constructs a lower bound. This is a function of theta. So this thing on the right-hand side, this is a function of the parameters theta. And what we proved last time was that that function is a lower bound of the log likelihood, right? And depending on what you choose for Q, you get different lower bounds. So one choice of Q, you might get this lower bound. For a different choice Q, you might get that lower bound. For a different choice Q, you might get that lower bound. And what the E step does is it chooses Q to get a lower bound that's tight, that just touches the log likelihood at the current value of theta. And then what the M step does is it chooses the parameters theta that maximizes that lower bound, right? So that was the EM algorithm that we saw. Now, I want to step through how you would take this, slightly abstract mathematical definition of EM and derive a concrete algorithm that you would implement, right, in Python. And so let's just step through this for the mixture of Gaussians model. So for the mixture of Gaussians model, we had a model for P of xi comma zi, which is P of xi given zi times P of zi, right? And our model was that z is multinomial with some set of parameters phi. Oh, and so the probability of zi being equal to j is equal to phi j, right? So phi is just a vector of numbers that sum to 1, specifying what is the chance of z being each of the k possible discrete values. And then we have that xi given zi equals j, that is Gaussian with some mean and some covariance, right? And what we said last time was that this is a lot like the Gaussian discriminant analysis model. And one trivial difference is this is sigma j instead of sigma, right? GDA, Gaussian discriminant analysis, had the same sigma every class, but that's not the key difference. The key difference is that in this density estimation problem, z is not observed, or z is a latent random variable, right? And which is why we have all this machinery of EM. So now that you have this model, let's see. Right. So now that you have this model, this is how you would derive the E and the M steps, right? So the E step is, you have Qi of Zi, right? But let me just write this as Qi of Zi equals J. This is sort of the probability of Zi equals J. I know this notation is a little bit strange, but under the Qi distribution, what do you want the chance of Z being equal to J, right? And so in the E step, you would set that to P of Zi equals J given Xi parameterized by all of the parameters. And we actually saw with Bayes' rule, right, how you would flesh this out, okay? And what we do in the E step is store this number, right, in what we wrote as Wij last time, okay? And so you remember, if you have a mixture of two Gaussians, maybe that's the first Gaussian, the second Gaussian, you have an example Xi here, so it looks like it's more likely to come from the first and second Gaussian, and so this would be reflected in Wij, that example is assigned more to the first Gaussian than to the second Gaussian. So what you implement in code is, you write code to compute this number and store it in Wij. And then for the M step, you would want to maximize over the parameters of the model, right? Phi, mu, and sigma. These are the parameters of the mixture of Gaussians of sum of I, sum of the Zi, right? And so the way you would actually derive this is you write this as sum of I. So Zi, takes on a certain discrete set of values. So Zi, turn Zi into J, right? So Zi can be, I guess, 1 or 2 if you have a mixture of two Gaussians. So you sum over all the indices of the different clusters of Wij times log of, the numerator is going to be times phi j. That's the numerator. And so, this term is equal to this first Gaussian term times that second term, right? Because this term is P of xi given zi, right? And the parameters. And this is just P of zi. Does that make sense? Okay. Right. And then it'd be take this and divide it by Wij. Okay. So I'm going to step you through the steps you would go through if you're deriving EM using that E step and M step we wrote up above. But if you're deriving this for the mixture of Gaussians model, then these are the steps of algebra, right? You would take. Okay. Sorry, I'm just realizing that. So in order to perform this maximization, what you will do is you want to maximize this formula, right? This big double summation with respect to each of the parameters phi, mu, and sigma. And so what you would do is take this big formula, right, and take the derivatives with respect to each of the parameters. So you take the derivative with respect to mu j, dot, dot, dot is that big formula on the left. Set it to 0, right, and take and then it turns out if you do this, you will derive that mu j should be equal to sum over I Wij over sum over I Wij. And this is what we said was how you update the means mu, right? The Wij's are the strength with which xi, so Wij is the, informally, this is the strength with which xi is assigned, right, to Gaussian j. And more formally, this is really P of zi equals j given xi and the parameters, right? And so, so you end up with this formula. But the way you compute this formula is by the rigorous way to show this is the right formula for updating mu j is looking at this objective, taking derivatives, saying derivatives equals 0 to maximize, and therefore deriving that equation for mu j, you know, by solving for the value of mu j that maximizes this expression. Right? And similarly, you know, you take derivatives respect of this thing, respect to phi, and set it to 0. Take derivatives of this thing, right, and set that to 0, and that's how you would derive the update equations in the m step for phi and for sigma as well. Okay. So for example, when you do this, you find that the optimal value for phi is let's see, yeah, there we go. We had this at the near the start of Monday's lecture as well. Okay. So this is a process of how you would look at the E-steps and M-steps I wrote up and apply it to a specific model, such as a mixtures of Gaussians model. And that's how you sort of, you know, solve for the maximization in the M-step. Okay? And so what I'd like to do today is describe the application of EM to a more complex model called the factor analysis model. And so it's important that, so I hope you understand the mechanics of how you do this, because we're going to do this today for a different model. Okay? Any questions about this before I move on? Okay, cool. So in order to, you know, foreshadow a little bit what we'll see when it comes down to the mixture of Gaussians model, the factor analysis model, which we'll talk about, which is what we'll spend most of the day talking about. In the factor analysis model, instead of zi being discrete, zi will be continuous, right? And in particular, zi will be distributed Gaussian. So in the mixture of Gaussians model, we had a joint distribution for x and z, where x was a discrete random variable. So in the factor analysis model, we'll describe a different model, you know, for p of x and z, where z is continuous. And so instead of sum over zi, this will be an integral over zi of dzi, right? So instead of sum, it becomes an integral. And it turns out that, yeah, well, right. Yeah, and it turns out that if you go through the derivation of the EM algorithm that we worked out on Monday, all of the steps with Jensen equality, all of those steps work exactly as before, meaning if you check every single step for whether zi was continuous, it'll work the same as before if you have changed the sum to an integral. Okay? All right. So, this up for a little bit longer. So I want to mention one other view of EM that's equivalent to everything we've seen up until now, which is, let me define J of theta comma Q as this. Okay, so is that formula you've seen a few times now. What we proved on Monday was L of theta is greater than or equal to J of theta comma Q. right? And this is true for any theta and any choice of q. Okay, so using Jensen's inequality, you can show that j for any choice of theta and q is a lower bound for the log likelihood of theta. So it turns out that an equivalent view of EM, as everything we've seen before, is that in the E step, what you're doing is maximize j with respect to q, and in the M step, maximize j with respect to theta, right? So in the E step, you're picking the choice of q that maximizes this, and it turns out that the choice of q we have will set j equal to L, and then the M step maximizes this with respect to theta and pushes the value of L even higher. So this algorithm is sometimes called coordinate ascent. If you have a function of two variables and you optimize with respect to this and optimize with respect to this, then you go back and forth and optimize with respect to one at a time. That's a procedure that's sometimes called coordinate ascent because you're maximizing with respect to one coordinate at a time. And so EM is a coordinate ascent algorithm relative to this cost function j, right? And on every iteration, j ends up being set to L, which is why you know that as the algorithm increases j, you know that the log likelihood is increasing on every iteration. And if you want to track whether the EM algorithm is converging or how it's converging, you can plot, the value of j or the value of L on successive iterations and see if it's validated it's going up monotonically, and then when it plateaus and isn't improving anymore, then you might have a sense that the EM algorithm is converging. Okay. All right. Okay, so that's it for the basic EM algorithm and mixture of Gaussians. What I want to do now is going to talk about the factor analysis algorithm. Right? All right, so the factor analysis algorithm will work. Actually, sorry. So I want to compare and contrast mixture of Gaussians with factor analysis we'll talk about in a little bit, which is for the mixture of Gaussians, let's say n equals 2 and m equals 100, right? So you have a data set with two features, x1 and x2, so n equals 2, and maybe you have a data set that looks like this. Then a mixture of two Gaussians would be a pretty good model for this data set, right? You can fit one Gaussian there, fit a second Gaussian there. You can kind of capture a distribution like this with a mixture of two Gaussians. And this is one illustration of when you apply mixture of Gaussians, in this picture, m is much bigger than n, right? You have a lot more examples than you have dimensions. Where I would not use mixture of Gaussians, and where you see in a minute factor analysis will apply, maybe if m is about similar to n, or even n is, or even m is much less than n. Okay, and so just for purpose of illustration, let's say m equals 30 and n equals 100, right? So let's say you have 100-dimensional data, but only 30 examples. And so to make this more concrete, many years ago, there was a Stanford PhD student that was placing temperature sensors all around different Stanford buildings. And so what you do is model, measure the temperature at many different places, right, around campus. But if you have 100 sensors, taking 100 temperature readings around campus, but only 30 days of data, or maybe 30 examples, then you would have 100-dimensional data because each example is a vector of 100 temperature readings, at different points around this building, say. But you may have only 30 examples of if you have, say, 30 such vectors. And so the application that the Stanford PhD student at the time was working on was he wanted to model P of x, right? So this is x as a vector of 100 sensors, 100 temperature readings. Because if something goes wrong, for example, because the bad case, if there's a fire in one of the rooms, then there'll be a very anomalous temperature reading in one place. And if you can model P of x, and if you ever observe a value of P of x that is very small, you would say, oh, it looks like there's an anomaly there, right? And we're actually less worried about fires on Stanford. The use case was actually, energy conservation. If someone unexpectedly leaves a window open in the building he was studying, and it was hot, and it's winter, and it's warmer inside the building, and cool air blows in, and the temperature of one room drops on an enormous way, he wanted to realize that something was going wrong with the windows or the temperature in part of the building. Okay? So for an application like that, you need to model P of x as a joint distribution over all of the different sensors, right? Actually, if you imagine maybe just in this room, let's say we have 30 sensors in this room, then the temperatures at the 30 different points in this room will be highly correlated with each other. But how do you model this vector of 100-dimensional vector with a relatively small training set? So it turns out that the problem with applying a Gaussian model, well, right, so one thing you could do is model this as a single Gaussian and say that x is distributed, right? And if you look at your training sets of 30 examples and find the maximum likelihood estimate of parameters, you find that the maximum likelihood estimate of mu is just the average, and the maximum likelihood estimate of sigma is this. Right? But it turns out that if m is less than or equal to n, then sigma, this covariance matrix, will be singular. Right? And singular just means non-invertible. Okay. I'll step for an illustration in a second. But if you look at the formula for the Gaussian density, right? So the Gaussian density kind of looks like this, right? Abstracting away some details. And when a covariance matrix is singular, then this term, this determinant term, will be 0. So you end up with 1 over 0. And then sigma inverse is also undefined, or it blows up to infinity, or depending on how you think about it, right? But so, the inverse of a matrix like 110, right, would be, I guess, 1 over 10, right? And an example of a non-invertible matrix or singular matrix would be this, and you can't actually calculate the inverse of that matrix, right? So it turns out that if your number of training examples is less than the dimension of the data, if you use the usual formula to derive the maximum likelihood estimate of sigma, you end up with a covariance matrix that is singular. Singular just means non-invertible, which means a covariance matrix looks like this. And so, the Gaussian density, if you try to compute P of x, you kind of get infinity over 0, basically, right? Oh, sorry, not infinity, actually 0 over 0. Sorry, doesn't matter. Right, it's all bad. And I think, let me just illustrate what this looks like, which is, let's say m equals 2 and n equals 2, right? right? So you have two-dimensional data, x1 and x2, and so n equals 2, and the number of training examples is equal to 2. So it turns out that, let's see, so you see me draw contours of Gaussian densities like this, right? Like ellipses like that. It turns out that if you have two examples in a two-dimensional space and you compute the most likely, maximum likely estimate of parameters of a Gaussian fit to this data, then it turns out that these contours will look like that, right? Except that instead of being very thin as I'm drawing it, it'll be infinitely skinny. So you end up with a Gaussian density where I can't draw lines, you know, of zero width on the whiteboard, right? But it turns out that the contours will be squished infinitely thin, so you end up with a Gaussian density, all of whose mass is on the straight line over there with infinitely thin contours that just, you know, is squished and centers on the plane, I guess, or on the line connecting these 2 points. And so this is, so first there are practical numerical problems, right? As in you end up with sort of 0 over 0 if you try to compute P of x for any example. And second, this very poorly conditioned Gaussian density puts all the probability mass on this line segment. And so any example, right, over there, just a little bit off, has no probability mass because, or has probability mass of 0, a probability density of 0, because the Gaussian is squished infinitely thin, you know, on that line. Okay? But you can tell, this is just not a good, this is just not a good model, right, for this data. So what we're going to do is come up with a model that will work even for these applications, even for a data set like this, right? There's actually I think the origins of the factor analysis model, one of the very early applications was actually a psychological testing, where if you have a, you know, administer a psychology exam to people to measure different personality attributes, right? So you might have 100 questions or measure 100 psychological attributes, but have a data set of 30 persons, right? And again, you know, doing psych research, running survey data is hard, right? So maybe you have a sample of 30 people, and each person answers 100 quiz questions. And so each person is gives you one example, right, x, and the dimension of this is 100-dimensional, but you have only 30 of these. And so if you want to model P of x, try to model how correlated are the different psychological attributes of people, right? Well, is intelligence correlated with math ability? Is that correlated with language ability? Is that correlated with other things? Then how do you build a model for P of x? Okay. All right. So if the standard Gaussian model doesn't work, let's look at some alternatives. One thing you could do is constrain sigma to be diagonal, right? So sigma is a covariance matrix, is an n by n covariance matrix. So in this case, it'd be 100 by 100 matrix. But let's say we constrain it to just have diagonal entries and zeros on the off diagonals, right? So these giant zeros, I mean, the diagonal entries of the square matrix are these values, and all of the entries off the diagonals will set to 0. So that's one thing you could do. And this turns out to be, to correspond to constraining your Gaussian to have axis-aligned contours, right? So this is a Gaussian with 0 off diagonals. This would be another one. Right? This would be another one. So these are examples of Gaussian, of contours of Gaussian densities with 0 off diagonals. So the axes here are x1 and x2, right? Whereas you cannot model something like this if your off diagonals are 0. And so if you do this, the maximum likelihood estimate of the parameters sigma j is pretty much what you'd expect, actually. The maximum likelihood estimate of the mean vector mu is the same as before, and this is maximum likelihood estimate of sigma j. Right? This is kind of not a huge surprise, kind of what you'd expect. And it turns out that, right, and so the covariance matrix here has n parameters. Instead of n squared, or about n squared over 2 parameters, right? The covariance matrix sigma now just has n parameters, which is the n diagonal entries. Now, the problem with this is that this modeling assumption assumes that all of your features are uncorrelated. Right? So this just assumes that any two features, xi and xj, are completely uncorrelated. And if you have temperature sensors in this room, it's just not a good assumption to assume the temperature at all points of this room are completely uncorrelated, completely independent of each other. Or if you measure psychological attributes of people, it's just not a great assumption to assume that the different psychological measures you might have are completely independent. So while this model would take care of the problem, the technical problem of the covariance matrix being singular, you can fit this model, on a 100-dimensional data set with 30 examples. You can fit this. You won't get, you can build this model. You won't run into numerical singular covariance matrix types problems. It's just not a very good model. Right? You're just assuming nothing is correlated to anything else. Oh, but something else that you can do is make an even stronger assumption. So this is an even worse model, but I want to go through it because there'll be a building block for what we'll actually do later, which is constraint sigma to be sigma equals lowercase sigma squared times I, right? And so constraint sigma to be not only diagonal, but to have the same entry in every single element. So now you've gone from, I guess, n parameters to just one parameter, right? And this means that you're constraining the covariance matrix to, you're constraining the Gaussians you use to have circular contour. So this is an example of what you can model. And this would be another example, right? And this is, and I guess this is another example. Okay, so you can model things like this, where every feature not only is, every feature is uncorrelated, but every feature further has the same variance as every other feature. And the maximum likelihood is this. Okay, and again, not a huge surprise, just the average over the previous values. So what we'd like to do is not quite use either of these options, right? Which assumes, really the biggest problem is assumes the features are uncorrelated. And what we'd like to do is build a model that you can fit even when you have very high dimensional data and a relatively small number of examples, but that allows you to capture some of the correlations, right? So if you have 30 temperature sensors in this room, probably there are some correlations, right? Probably this side of the room temperature is going to be correlated, and that side of the room temperature is going to be correlated, and maybe the ambient temperature in this whole building, or the temperature of this room probably goes up and down as a whole, but maybe some of the lamps on the side heat up that side of the room a bit more. So there are correlations, but maybe you don't need a full covariance matrix either. So what factor analysis will do is give us a model that you can fit even when you have 100-dimensional data and 30 examples that captures some of the correlations, but that doesn't run into the uninvertible covariance matrices that the naive Gaussian model does. Okay. All right. So let me actually just check any. Let me describe the model. Let me just check any questions before I move on. Oh yeah.
Would it be possible to have some prior on the Gaussians in order to avoid these problems?
Oh sure, yes. Yes, there is one thing you can do. A common thing to do is to apply a Wishart prior, and what that boils down to is add a small diagonal value to the maximum likelihood estimate. it kind of, in a technical sense, it takes away the non-invertible matrix problem, but it's actually not the best algorithm for a lot of the types of data. The Wishart or inverse Wishart prior, yeah, add a, basically take the maximum likelihood for sigma and add, some constant to the diagonal. It takes care of the problem in a technical way, but it's not the best model for a lot of data sets I see, for example. Yeah.
Why do we even think about option 2 when we know the option 1 doesn't?
Oh yes, why do you think about option 2 when it's like even worse than option 1? Yes, option 2 is not a good option, but I need to use this as a building block for factor analysis. So you see this is a small component of see, I actually plan these things out, Cool, yeah. And maybe actually to give broader context, just to mention, just to mention some of the things I see, actually, it's actually, the machine learning work evolves all the time. You should find it fascinating. But if you look at a lot of the big tech companies, a lot of the large tech companies are all like working on exactly the same problems, right? Every large tech company, software AI company is working on machine translation. Every one of them works on speech recognition. Every one of them works on face recognition. And I've been part of these teams myself, right? And I think it's great that we have so much progress in machine translation because there's so many people in so many large companies working on machine translation. So I'm actually really happy to see so much progress in these problems that every single large tech company, large software AI-ish tech company works on. One of the fascinating things I see is that because of all this work in the large tech companies working on very similar problems, one of the really overlooked parts of the machine learning world is small data problems, right? So there's a lot of work on big data. If you're Brazilian, English and French and Chinese and Spanish sentences, the certain class model doesn't work. And I think there's actually a lack of attention, like a disproportionately small amount of attention on, small data problems, where instead of 100 million images, you maybe have 100 images. And so some of the teams I work with these days, actually like Landing AI, I actually spend a lot of my time thinking about small data problems because a lot of the practical applications of machine learning, including a lot of things you see in your class projects, are actually small data problems, right? I think when Anand works with a healthcare system, works at Stanford Hospital, for some of the problems, you only have 100 examples, or maybe 1,000, or maybe 10,000. You don't have 1 million patients with the same medical condition. And so I think that a lot of these models, and again, earlier this week, I was using slightly modified version of factor analysis on a manufacturing problem at Landing AI, right? And I think a lot of these small data problems are actually where a lot of the exciting work is to be done in machine learning, and it's somehow, it feels like a blind spot, or it feels like a gap of a lot of the work done in the AI world today. Go ahead.
Is there some reason why we don't use the same algorithms for like small data problems as we use for the big data problems? Like, I understand why not all big data like algorithms can be used in small data, but why can't all small data be used for big data?
Yeah, why don't we use the same algorithms as one big data? It turns out that, it turns out if you look at the computer vision world, right, there's a data set that everyone's working on. Now we're past it. We don't really use it anymore, called ImageNet, which had 1 million images. And so there are tons of computer vision architectures that have been heavily designed for the use case of if you have exactly 1 million training examples. And it turns out that the algorithms that work best, if you have 100 training examples, is, looks like it's different than the best learning algorithm. And I think, and so I think right now, I think the machine learning world, we are not very good at understanding the scaling. The best algorithm for one training example, as far as we are able to invent algorithms as a community, is different than best algorithm for 1,000, best for 1 million. It's actually different than, actually, and Facebook published a paper recently with 3.5 billion images, which was cool. This is very large, right? So I think we don't actually have a good understanding of how to modify our algorithms to have one algorithm work on every single point of the spectrum, going from one example to like 1 billion examples. And so there's a lot of work optimizing for different points of the spectrum. And I think there's been a lot of work optimizing for big data, which is great. Built some of these large systems that handle like whatever, right, petabytes of data a day. That's great. But I feel like relative to the number of application opportunities, there's a lot of work on small data as well that I find very exciting. And I think of this as an example The reason I was using this, like literally, well, modified version of this earlier this week on the manufacturing problem is because there isn't that much data in those scenarios, right? Cool. All right, that's off topic, but let's go and describe. Well, hopefully, maybe yeah. So this stuff does get used, right? So let's talk about the model. So similar to EM for mixture of Gaussians, I'm going to define a model with P of xz equals P of x given z times P of z, and z is hidden. Okay, so that's the framework, same as mixture of Gaussians. So let me just define the factor analysis model. So first, z will be drawn distributed according to a Gaussian density, where z is going to be an RD, where d is less than n. And again, to think about it, maybe you can think of it as d equals 3, n equals 100, m equals 30. Okay, but I guess maybe just as a concrete example to think about it. And what we're going to assume is that x is equal to mu plus lambda z. This is the capital Greek alphabet lambda plus epsilon, where epsilon is distributed Gaussian with mean 0, and covariance psi so the parameters of this model are mu, which is n-dimensional, lambda, which is n by d, and psi, which is n by n, and we're going to assume that psi is diagonal. Okay? And so, let's see, this second equation, an equivalent way to write that, equivalently, is that given the value of z, the conditional distribution of x, right, x given z, this is Gaussian with mean given by mu plus lambda z and covariance psi. Okay, so once you've given z, once you've sampled z, so this is p of z and this is p of z and this is p of x given z, right? So given z, x is computed as mu plus lambda z, so this is just some constant, and then you add Gaussian noise to it. And so this equation, an equivalent way to defining this equation is to say that the mean of x conditioned on z is this first term, right? Since that's the mean. And the covariance of x given z is given by this, additional term psi, by that noise term that you add to it. Okay? So let me go through a few examples. And I think the intuition behind this model is if you think that there are 3 powerful forces driving temperatures across this room, maybe one powerful force is just what is the temperature, here in Palo Alto? What's the temperature here at Stanford? And another powerful force is how bright are the lights on the left side of the room, and how hot does it heat up this side of the room? And another is how hot does it heat up the right side of the room, right? So if, let's say there are 3 main driving factors affecting the temperature of this room, then that's when D would be equal to 3. That you assume that there are 3 things in the world that drive the temperature of this room. This 3-dimensional, which is the temperature in Palo Alto, kind of around this area, how bright are the lights there, and how bright are the lights there. And you try to capture that with 3 numbers. Given those 3 numbers, right, given Z, the actual temperature for the 100 sensors we scatter around this room will be determined by each sensor, right? So we plant 30 temperature sensors all over this room. Each sensor we plant will measure an actual temperature that's a linear function of those 3 powerful forces. And if it's a sensor on that side of the room, it will be affected more by how bright are the lights on that side of the room. If it's a sensor near the door, it will be more affected by the temperature outside, temperature here in Palo Alto, right? But so x will be a linear function. This first term I underlined. But rather than just that term, there's additional noise, right? So each sensor has its own noise term, which is governed by this additional noise term, epsilon. And the assumption that this matrix psi is diagonal is saying that after you compute the mean, the noise that you observe at each sensor is independent of the noise at every other sensor. That make sense, right? That maybe the sensor, you know, up there, right? Maybe it's just noisy or something, this gust of wind, right? But you assume that the noise of observed at different sensors is independent. The additional epsilon error term has a diagonal covariance matrix given by psi. Okay, so you can think of that as what factor analysis is trying to model. Okay. So let me just go through a couple examples of the types of data factor analysis can model. All right, and again, by the constraints of whiteboard, I'm going to have to go low dimensional here, right? So actually, let me go through a couple examples. So let's say z is R1 and x is R2. So in this example, I guess d is equal to 1, n is equal to 2, and let's say m is 7, right? Just. So what would be a typical sample generated by, you know, what would be an example of a type of data that this can model? So this, actually, let me just draw this here. All right. So this would be a typical sample of Zi, right, which is, you know, so this is Z is just drawn from a standard Gaussian. So I guess Z is just Gaussian with mean Z-run unit variance. So that's the number line. And if you draw 7 points from a Gaussian, you know, maybe you get a sample like that. Okay. And now let's say lambda is 2, 1. And let's just say mu is 0, 0. Okay. So now let's compute lambda x plus mu, right? So given a typical sample like that, if you compute lambda x plus mu, this will now be an R2, right? So here's x1, here's x2. We're going to take those examples and map them to a line as follows. Right, where these examples on R1, so, oh, excuse me, lambda z plus mu. Okay, so this is just a row number. And so lambda z plus mu is now two-dimensional, right? Because lambda is a 2-by-1 matrix. Okay, so you end up with, so this would be a typical sample, typical random sample of lambda z plus mu. And it's a two-dimensional data set, but all of the examples lie perfectly on a straight line. Okay. Then finally, let's say that psi, the covariance matrix, is equal to this as a diagonal covariance matrix. And so this covariance matrix corresponds to x2 having a bigger variance than x1, right? And so, you know, this I guess the density of epsilon has ellipses that look a little bit like this. It's taller than wide. The aspect ratio should technically be 1 over root 2 to 1, right? Because standard deviation is would be root 2, I guess. And so in the last step of what we're going to do, x equals lambda z plus mu plus epsilon, we're going to take each of these points we have and put a little Gaussian contour. You know, there's that shape. There's this I'm just drawing one contour, I guess. There's this shape and just puts it on top of this. And if you sample 1 point from each of these Gaussians, then maybe you get this example, this example, this example, this example, So what I just did was look at each of the Gaussian contours and sample a point from that Gaussian. And so the red crosses here are a typical sample drawn from this model, okay? Right? And so if you have data that looks like this, that looks like the red crosses, the z's are latent random variables, right? And when you get the data set, you can't actually see z. So what you actually see is just the red crosses. That's your training set. And if you apply the factor analysis model with these parameters, then via EM and so on, hopefully you can find parameters that models this data set pretty well. But hopefully this gives you a sense of the type of data set this could generate. And so one way to think of this data is you have two-dimensional data, but most of the data lies on a 1D subspace. So this is how to think about it. You have two-dimensional data, since n is 2, but most of the data lies on a roughly one-dimensional subspace, meaning it lies roughly on a line, and then there's a little bit of noise off that line. Okay? All right, let me quickly do one more example, because these are high-dimensional spaces, and I think it's useful to build intuition. All right, so let's go through an example where z is in R2, x is in R3, and let's use m equals 5. So d equals 2, n equals 3. Okay? So with a different set of parameters, let's look at the type of data you can generate factor analysis, which is here's z1 and z2. Z is distributed Gaussian, standard Gaussian in 2D, so it'll be a circular Gaussian. So maybe this is what a typical sample, right, looks like. If you sample sort of z1 and z2 from a standard Gaussian, right, that would be a typical sample in z1 and z2. So now, all right, I'm going to do a demo. Let me take these 5 examples and just copy them to this piece of paper, okay? So, all right, there, right? Transferred it from the whiteboard to this piece of paper, to this brown cardboard. So now you have z1 and z2 in a two-dimensional space. What we're going to do is compute lambda z plus mu. And this will be 3 by 2, and this will be 3 by 1. So what this computation will do as you map from z in 2 dimensions to lambda z plus mu is you're going to map from 2-dimensional data to 3-dimensional data. In other words, you're going to take the 2-dimensional data lying on the plane of the whiteboard and map it, check out this cool animation, into the 3-dimensional space of our classroom. And then the last step is for each of these points in this 3-dimensional space, like x1, x2, x3, right, we'll have a little Gaussian bump that is axis aligned because epsilon is the features, the components of epsilon are uncorrelated, and take each of these 5 points and add a little bit of fuzziness, add a little bit of Gaussian noise to it. And so what you end up with is a set of red crosses. Right? You end up with a few examples, add a little bit of noise, you end up with, except that they would have a bit of noise off this plane as well. Right? But so what the factor analysis model can capture is if you have data in 3D, right, in this 3D space, but most of the data set lies on this maybe roughly 2-dimensional pancake, but there's a little bit of fuzziness off the pancake, right? So this would be an example of the type of data that factor analysis can model. Okay? All right, cool. And the intuition is really factor analysis can take very high dimensional data, say 100-dimensional data, and model the data as roughly lying on a 3-dimensional, 5-dimensional subspace with a little bit of fuzz, with a little of noise off that low-dimensional subspace. Okay. Great. So So let's talk about, yeah.
Sorry, does this not work as well if it's not lying on a low-dimensional subspace?
Oh, right. Does not work as well if the data is not lying on a low-dimensional subspace. Let's see. So even in 2D, if you have this data set, right, you actually have the freedom to choose Gaussian noises like that, in which case you can actually model things that are quite far off a subspace. Yeah, I think when you have very high dimensional data sets, it's actually very difficult to know what's going on because you can't visualize these very high dimensional data sets. And you also don't have enough data to build very sophisticated models. So I feel like, yes, if the data actually does not roughly lie in the subspace, then this model, may not be the best model. But when you have such high dimensional data and such a small data set, you can't fit very complex models to it anyway, so this might be pretty reasonable. Right? All right, cool. All right. So, so it turns out that the derivation of EM for factor analysis is actually one of the trickiest EM derivations in terms of how you calculate the E step and how you calculate the M step. The whole algorithm is described, every single step is stepped through in great detail in the lecture notes. But what I want to do is give you the flavor of how to do the derivation and to especially draw attention to the trickiest steps so that if you need to derive an algorithm like this yourself or maybe a different Gaussian model, that you know how to do it, but I won't do every step of the algebra here. Right? So in order to set ourselves up to derive factor analysis, E and M for factor analysis, I want to describe a few properties of multivariate Gaussians. So let's say that X is a vector, and I'm going to write this as a partition vector, right, in which if there are R components there and S components there. So X1 is in RR, X2 is in RS, and X is in R plus S. Okay? So if X is Gaussian with mean mu and covariance sigma, then let's similarly let mu be written as this sort of partition vector. Right? Just break it up into two subvectors corresponding to the first R components and the second S components. And similarly, let's let the covariance matrix be partitioned into these four diagonal blocks where I guess this is R components, this is S components, this is R components, this is S components. So all this means is you take the covariance matrix and take the top leftmost R by R elements and call that sigma 1, 1, right? And similarly for the other subblocks of this covariance matrix. So in order to derive factor analysis, one of the things you need to do is compute marginal and conditional distributions of Gaussians. So the marginal is, what is P of X1? Right? And so if you were to derive this, the way you compute the marginal is to take the joint density of P of X, right? And you can write this as P of X1, X2, because X can be partitioned into X1 and X2, and then integrate out X2 of P of X1, X2, right, dx2, and this will give you P of X1, right? And if you plug in the Gaussian density, the formula for the Gaussian density, if you plug in, I guess, 1 over 2 pi to the n over 2 is equal to 1/2, right, e to the minus 1/2, x1 minus mu1, x2 minus mu2, right? If you plug this into P of X1 comma X2 and actually do the integral, then you will find that the marginal distribution of X1 is given by x1 is distributed Gaussian with mean mu1 and covariance sigma 1, 1. So it's kind of not a shocking result that the marginal distribution is given just by that and that, right? And again, the way to show it rigorously is to do this calculation, but it's actually not shocking, I guess, that's what you would get, okay? And then the other property we'll need to use is a conditional, which is given the value of x2, what is the conditional value of x1? And so the way to do that would be, in theory, you would take p of x1 comma x2, divide by p of x2, right, and then simplify. And it turns out you can show that x1 given x2 is itself Gaussian with some mean and some covariance, which I'm going to write as mu of 1 given 2 and sigma of 1 given 2, where mu of 1 given 2 is, but this is one of those formulas that I actually don't manage to remember, but every time I need it, I just look it up. And it's written in lecture notes as well, so. X2 minus 2, 2. Oops. Okay. So that's how you compute marginals and conditionals of a Gaussian distribution. Okay. So using these properties of the multivariate Gaussian density, let's go through the high-level steps of how you derive the EM algorithm for this. All right. Step 1 is let's compute. Actually, let's excuse me. Let's derive what is the joint distribution of p of x and z, right? And in particular, it turns out that if you take z and x and stack them up into a vector like so, z and x viewed as a vector will be Gaussian with mean with some mean and some covariance, because x and z jointly will have a Gaussian density. And let's try to quickly figure out what are this mean and that covariance matrix. So that was a definition of these terms. And so the expected value of z is equal to 0, because z is Gaussian with mean 0 and covariance identity. And the expected value of x is equal to the expected value of mu plus lambda z plus epsilon. But z has 0 expected value, epsilon is 0 expected value, so that just leaves you with mu. And so this mean vector, mu xz, is going to equal to 0 mu. Right, and so this is d-dimensional, and this is n-dimensional. Okay. And it turns out that, let's see. And it turns out that you can similarly compute the covariance matrix sigma, right, where this is d dimensions and this is n dimensions. It turns out that if you take this partition vector and compute the covariance matrix, the 4 blocks of the covariance matrix can be written as follows. And you can, one at a time, derive what each of these different blocks look like. And let me just do one of these, and let me just derive what sigma 22, the lower right block is, and the rest are derived similarly and also fleshed out in the lecture notes. So the way you derive what this block is like is that you say sigma 22 is x minus ex transpose. And so if I plug in the definition of x, that would be lambda z plus mu plus epsilon minus mu times the same thing. So that's x minus ex. So that's x minus ex. Okay, because the expected value of x is mu. So the mu's cancel out. And then if you do the quadratic expansion, I guess this becomes expected value of, let's see, lambda z times each of these two terms transpose plus, it's sort of, you know, a plus b times a plus b, right? Is a times a plus b, b times a, b plus b. You get 4 terms as a result. And so the first term is lambda z times lambda z transpose, which is this, plus lambda z epsilon transpose plus epsilon. And so this term has 0 expected value because epsilon and z both have 0 expected value and uncorrelated. So this is 0 on expectation. And so you're just left with expected value of lambda zz transpose, lambda transpose, plus the expected value of epsilon transpose, right? And so by the linearity of expectation, you can take an expectation inside the matrix multiplication. So this is lambda times the expected value of zz transpose times lambda transpose plus, and this is just the covariance of epsilon, right? Which is psi. And then because z is drawn from a standard Gaussian with identity covariance, that expectation in the middle is just the identity. So that's lambda transpose plus psi. Okay? So that's how you work out what is this lower right block of this covariance matrix. I know I did that a little bit quickly, but every step is written out more slowly in the lecture notes as well. Okay? And it turns out that if you go through a similar process to figure out, you know, one at a time, using a similar process, what are the other blocks of this covariance matrix, you find that the other blocks of this covariance matrix are identity, lambda transpose, and the one we just worked out. Okay, so that's the one we just worked out. But so that is the covariance matrix psi. So where we are is that we've figured out that the joint distribution, the joint density of Zx is Gaussian with mean given by that vector and covariance given by that matrix. Okay. And so what you could do is write down, right, p of xi and try to take the, so P of xi will be this Gaussian density. And what you could do is take derivatives of the log likelihood with respect to the parameters and set the parameters to 0 and solve. And you find that there is no known closed form solution. There is actually no closed form solution for finding the values of lambda and psi and mu that maximizes log likelihood. So in order to fit the parameters of the model, we're instead going to resort to EM. Okay? And so in the E step, so let's first derive what is the E step, which is in the E step, you need to compute this, right? Now, Zi here is a continuous random variable. When we're fitting a mixture of Gaussian distributions, Zi was discrete, and so you could have a list of numbers represented by, Wij that just have a vector storing what is the probability of each of the discrete values of Zi. But in this case, Zi is a continuous density. So how do you represent Qi of Zi in a computer? It turns out that using the formulas we have for for the conditional distribution of a Gaussian, it turns out that if you compute this right-hand side, you find that Zi given xi, this is going to be Gaussian with some mean and some covariance. Right? Where, it's basically those formulas. Mu of Zi given xi is equal to, if you kind of take that formula and apply it to our thing here, is 0 plus lambda transpose and okay, so these equations are exactly these two equations, right? Mapped to that big Gaussian density that we have. Okay, so what you would do in the E step is compute this and compute this vector and compute this matrix, and store these as variables. And your representation of the Qi is that Qi is a Gaussian density, right, with this mean and this covariance. So this is what you actually compute to represent Qi. Okay. So step 2 was derive the E step. And step 3 is derive the M step. And the derivation of the M step is quite long and complicated. But I want to mention just a key algebraic trick you need to use when deriving the M step. So we know from the E step that Qi of Zi is that Gaussian density, right? So it's 1 over 2 pi to the d over 2, that thing, and e to the negative 1/2 dot dot dot, right? So that's the formula of Qi. It turns out that in the M step, there'll be a few places in the derivation where you need to compute something like this. And one way to approach this would be to plug in the density for Qi, which is, so you end up with this, 1 over root 2 pi to the d over 2 sigma, and so on, e to the negative 1/2 dot 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 times Zi dzi, and then try to compute this integral. It turns out there's a much simpler way to compute this integral. Anyone know what it is? All right, cool, awesome, right? Expected value. So the other way to compute this integral is to notice that this is the expected value of zi when zi is drawn from qi, right? So the definition of expected value of random variable is expected value of z is equal to integral over z probability of z times z dz, right? That's what the expected value of a random variable is. And so this integral is the expected value of z with respect to z drawn from the qi distribution. But we know that qi is Gaussian with a certain mean and a certain variance. And so the expected value of this is just mu of zi given xi, right? It's that thing that you've already computed in the E step. Does that make sense? And so when students derive the M step, for EM implementations of Gaussians, one of the key things to notice is when are you actually taking an expected value with respect to a random variable, in which case it's just the value you've computed already, and when do you need to plug in this big complicated integral, which can lead to very complicated, very intractable calculations. Okay, so just whenever you see this, think about whether you need to be expanding a big complicated integral or if it can be interpreted as an expected value. And so for the M step, is really, the M step is right. So that's the M step. And if you rewrite this term as sum over I, the expected value of zi drawn from qi of this right? It turns out that if you go ahead and plug in the Gaussian density here, actually, one rule of thumb for whether or not you should plug in a complicated integral or plug in a Gaussian density, this is just a rule of thumb after doing this type of math a long time, is see if there's a log in front. If there's a log in front of a Gaussian density, because the Gaussian density has an exponentiation, right? The Gaussian density is 1 over e to the something. So whenever there's a log in front, the log and exponentiation cancel out, and this equation simplifies. So one trick as you're doing these derivations is just see if there's a log in front of a Gaussian density. And when there is, if you go ahead and plug in the formulas for Gaussian density, the log will simplify that. And what you end up with is the log of a Gaussian density ends up being a quadratic function. A quadratic function of the parameters. And if you take the expected value with respect to a Gaussian density with respect to a quadratic function, this whole thing ends up being a quadratic function. And then you can take derivatives of that equation with respect to the parameters, with respect to mu of that whole thing, set it to 0, and then solve, and it'll be roughly level of complexity of maximizing a quadratic function. Okay? Hope that makes sense. The actual formulas are a little bit complicated, so I'll leave you to look at the actual formulas in lecture notes, but I think the takeaway is don't expand this integral, and when you are deriving this, plug in the Gaussian densities here because of the log, and this is simplified. Okay? And the details are written in lecture notes. So let's break for today. Best of luck with the midterm, and seriously, I hope you guys do well. All right, I'll see you guys in a few days.